So once the beamer comes back on, but everybody managed to do either one or even both. Let's see if it loads. There we go, slowly but steadily. So most of the errors you run into are people not loading the packages or not using the commands correctly. Again, the more you do it, the easier it will become, and it's again sensitive to using a capital T or a small t, etc. So occasionally you will have to use, your supervisor might ask you to use partial correlations. And so partial correlations are like your correlations you had before, but then you want to control for a third variable. That variable is usually referred to as z. So in this case, I've done an example for you, and so you need a separate package for it, which is ppcore, which does partial correlations. And so then the command is pcore test rather than core test, core.test. So it's similar to what you had before, but then now it has a p for partial. We have to say which one is our x variable, which one is our y variable, and which is the variable we want to control for. So in this case, we want to see if education correlates with prestige after accounting for income, for how much money people make. Yeah. And what it then will print is the estimate of the partial correlation coefficients. So that's like an R value, so it can go from 0 to 1. That's a very high number, as you can see, so 0.76. So quite a strong association after controlling for income. So the number of years you've studied for something correlates with how the sociologist rate the profession positively, as you might expect. It gives you a p-value, it gives you the statistic, so that would be like a t value or a z value, depending on the sample size. You can read in the manual, but mostly will be t values. It gives you the sample size. You get the degrees of freedom. You have to do the calculations by hand. So you have to subtract 2, and then for every case control variable, you would subtract another degree of freedom. So you have to go back and look at how to calculate degrees of freedom, or you can just report sample size. That would also be acceptable as long as people know how many variables you've controlled for. They can adjust for it, and it tells you the method. And so I think GP stands for group, in case you want to have multiple groups. So again, look at further commands. This is just an example. Again, if you want to run partial correlations, you can do and find out more by yourself. That's how you do a partial correlation. Now, linear regression is similar to the correlation coefficient, as you might recall. It's just now we say that one is x and one is y, and in the same in the base association, the beta from regression is the same as your correlation coefficient. So the standardized slope is the same as your correlation coefficient when you do an orderly squares regression. But we can then start adding more and more variables, and regression allow for some things which you can't do with just correlations. Yeah. So when would you use linear regression? Any answers from you? Which scenarios would you use linear regression?
So when there's no predictor and a hierarchy for the whole time, is that right?
What?
Is when you're not predicting an outcome, there's a hierarchy as well by respondents linear.
So I think you're getting in the right direction. So what we usually want to do is we want to make hierarchical tables. So we want to add, in step 1, we want to add one variable. In step 2, we want to add another variable. So you've come across these papers also in your journals where people start adding things to basically show how robust relationships are. But basically, it's when we're interested in the association between two continuous variables. And it's a long history, but I've mentioned also last time, ANOVA and regression are to some degree related, or actually actually the same. The F-tests are similar, and that's just because ANOVA comes from the experimental tradition, and regression comes more from the biometrical things. So the first thing which people were correlating were heights. So for example, if you have a continuous variable and you want to associate that with a continuous variable, you would use linear regression, and then you would build tables to add more and more things. If you have an experiment with conditions, then most of the time people would opt for ANOVAs, but if you've seen for last time, the LM command, which is a linear model, is the same for, it will also give you the F-test, and will also be the same. And you can get a regression or an ANOVA the same way, just by using dummy codes, for example. You might recall dummy codes. So you suppose you have 4 conditions, you make it into 3 dummies, and you add those dummies to the regression, And that conclusion will be the same as when you would have done an ANOVA with condition as a factorial variable. Yeah? But mostly it's when we have continuous variables as outcome measure and also as predictor variables. So how would we run a very basic one? And so this is just a one variable, so I've called it module education. You should remember the lm command from ANOVA, so it's the same type of a thing. So prestiges are dependent, the tilde gives the formula, and then education is the independent, and we have to tell it where the data is located, which is prestige. And then you have to use summary to summarize your model, because actually underneath the hood it will do all sorts of things. It will calculate residuals, it will calculate coefficients, it will calculate predicted variables, it will calculate all sorts of other things. And we are just interested in the beginning in the summary of our model. And so use the summary command for that. And you can inspect module education, and you can see what is all, what type of, with the $sign, what is all stored under module education. So what it's done is it will print the formula which it's used. Yeah, so that should be the same, hopefully, as we get here, because otherwise something has gone horribly wrong. It tells us the data. It tells us the residuals. If you're super clever, you can sort of already see if that's more or less normally distributed, but the residuals are sort of the trash bag. And we'll print the residuals, which will print the median and the mean, and we'll print just the distribution. And then it will print the coefficients. So this is the intercept. So basically, if you imagine it graphically, it's how much you move up or down on the axes. And it will print the slope, which is the b. And so this is a b and not a beta because it's not standardized. And this is the slope, and that's the estimate for the slope. And based on that, we have a regression fit, as you've seen on the charts. So you basically have a cloud with a scatter plot, and you have a line going through it. And that is your fit line, and that's the best fitting line according to regression. Yeah? Does that ring a bell? Going back? So that's the estimate, and then it will print the standard error of the estimate. And so if you can do some quick arithmetic in your head, so roughly 2 times the standard error gives you the 95% confidence interval on whether that overlaps with 0 or not. But you can also look at the t values, and this is the probability of the t-value, and again they use the star notation for significance. And we should expect it to be significant because I've already shown you that the partial correlation coefficient is highly significant, so we're expecting something highly significant here. Some things have dropped off, but we'll come to that in a bit. Now, more importantly, perhaps, there's a whole host of assumptions to that. Actually, what's printed off is just the r square and the addition r square. I'll resize it for a slide, but you'll have some examples later. So there's many assumptions, and I'll just run through them, and then we can have a short break, and then I think you have to go. And it's important that you are aware of these assumptions and that you sort of know what the potential remedies are. It will become quickly complex, but you should also then be aware of the limitations of your OLS regression model. So linear, think back to your data source. And it also relates to this also relates to issues of multicollinearity and with issues with measurement error. So if you plot the raw data and you find a parabola, for example, then it's not a linear relationship. Or if you find an exponential function, then probably a linear way is not a linear regression is not the route to go. Then you should transform your data, or you should think a cubic function or a parabola function in order to get a better understanding of your data. Also, if things are not perfectly measured, then there will be that will affect which degree it's linear. So that's why I've listed in this case. Normality. So I was saying with residuals, you can already sort of guesstimate. You're hoping that they are normally distributed around 0 and symmetrical, so that it's quite nice to each side, and they form a nice bell curve, so that the errors you make are equal on one side as on the other. So it's not overestimating hugely on one side and not on the other side, and that's what why we have these assumptions about normality. Again, you might recall the good thing is the central limit theorem. The larger the sample size, the less worrisome it becomes. But again, if it's completely bimodal or completely messed up, and you look at the plot, then you have a problem. Yeah. Again, what we heard with correlations, homoscedasticity, so the variance of the errors should be constant. So that's the equivalent of the homogeneity of variance assumption which you came across with ANOVA. Yeah. So, and in this case also the combination, so if you have multiple variables, also their combination should be, the error should be constant, which you make at the beginning of the slope, so to speak, as towards the end of the slope. Everybody understands this principle? Independence. Now, often also you will have issues in terms of autocorrelation. Things or should be normally independently sampled. So I've talked to you about multi-level models. There might be scenarios where that's not the case because children are more similar than expected by chance if they're in the same class group, for example, as opposed to when we take child A from group A and child B from group B. If we randomly would sample them, that would be better than all the children from class A, all the children from class B, because that doesn't account for independence of observation. And there's ways to test things, and mostly also that's one of the reasons which I won't cover, but if you ever run into problems with longitudinal data, that's an issue there in terms of autocorrelation. So you try to detrend to data and try to account for any type of, because over time, things might just correlate with each other through chance, and to take away that trend, you would detrend your relationships and get rid of problems with autocorrelation. So if everything is independently sampled and independently observed, then there's no issues. But there could be cases where that's not the case, or it could be that you have some autocorrelation in your data empirically, and then you should account for that. You might have heard of the Durbin-Watson test, and we'll come to that in a bit. But perhaps first we should have a break, and you can read more here. There's a paper dealing with all the assumptions for linear regression. So we have a 5-minute break. Is that okay? Or so just 5 minutes, and then we'll continue.